Hi everyone, back for chapter 2. So the beginning of chapter 2 is really about the atomic theory of matter, and it goes through kind of the historical development of the model of the atom with the law of conservation of mass, the law of multiple proportions, Dalton's atomic theory, the discovery of the structure of the atom with J.J. Thomson's experiment, the milk and oil drop experiment, Rutherford's gold foil experiment. So I think I'm just going to have you read through these slides, read through the pages in the textbook that relate to this. And then I'm also going to point you to the one of the videos that's in the helpful video list, and it's about the atomic theory and the development of the model of the atom. That might be enough of the, the details that you really need for the development of that theory. So I'm really going to start here on page 7, where we get kind of into the nitty-gritty of the atom and its subatomic particles. And so where I'll start is with a really simple model of the atom, and I'm going to have my electron cloud here. I'm going to have my nucleus here in the middle, and we're going to just talk a little bit about the subatomic particles. So within the nucleus, all right, that's at the center of the atom, you're going to have, so in the nucleus, you're going to have protons and neutrons. Protons have a positive charge. Neutrons have no charge. They're neutral. And then outside of the nucleus, you're going to have what we call the electron cloud, or the electrons, and the electrons carry a negative charge. All of the mass of the atom comes from the nucleus, where your protons and neutrons are. I'm going to go back a slide here. So this kind of just gives you some of the relative sizes and masses of the subatomic particles here on this slide. And so we know that the protons are positive, we know the neutrons are neutral, and the electrons are negative. And these are their relative masses. That's not the actual mass in any unit that you're probably very familiar with. So it's not a gram or an ounce or anything of that nature. It's really called an AMU. So it's really a relative mass. So what it's saying is that the mass of a proton and neutron are very, very close to each other. The neutron is a tiny bit larger, and the mass of an electron is minuscule compared to the mass of the protons and the neutrons. But we call them 1 AMU. We say that each proton contributes 1 atomic mass unit to the mass of the atom, and 1 neutron contributes 1 atomic mass unit. And very often we just call it 1 AMU and 1 AMU. But there is this tiny distinct difference between those two masses, where the neutron is a tiny, tiny bit heavier. So we're going to look at what the element symbol tells us in terms of these protons, neutrons, and electrons. So the larger number, it can't say that it's always in the top left corner. It really depends upon what resource you're looking at, what periodic table you're looking at. Sometimes the smaller number is on top. And so anyway, we call the larger number the mass number, or the atomic mass, and it's the number of protons plus neutrons. And then the atomic number is the number of protons or electrons, not protons added to electrons. The letter is the symbol of the element that you would find on the periodic table. So elements are represented by one or two letters, for which the first letter is always capitalized, and C is a symbol for carbon, so you just have the one letter. Atomic number, as it's said above, number of protons and neutrons. All atoms of the same element have the same number of protons. That's important. All atoms of the same element have the same number of protons. And the proton number is called Z. All right. So I'm going to go through a couple of examples of this with you on the next slide. Sorry, the next slide. So let's take an atom of sodium. So an atom of sodium, I would find something like this on the periodic table. Small number on top, larger number on the bottom. Again, don't, always think that it will be set up this way. It could be the larger number on top, the smaller number on the bottom, but there's a way of distinguishing what number means what. So for this symbol, I have the atomic number on top, and the atomic number is equal to the number of protons. So the number of protons represented by this isotopic symbol, which is what I call that, and we'll talk more about isotopes as we go on. So it has 11 protons. And if it's neutral, which this is, you don't see a charge here in this right upper corner, then the number of electrons is going to be the same. And the number of neutrons is always going to be this atomic mass number, okay, the larger number below, rounded to a whole number, because you can't have a portion of a neutron. So it would be 23 minus the atomic number, which is equal to 12. I had that number down there to help you remember that. Okay, so let's go on to our next example. Just try one more quick. So this one, the number on top, the smaller number, is the number of protons. It's 31. I see no charge here, and I'll talk about that in a minute. And so the number of electrons is also 31. And so my number of neutrons in this example, I calculated it out before, is 39. And where does that come from? It would come from, I would round up because this is at 0.7. So I round this up to the nearest whole number. Whoops, sorry. So it would be 70 minus the atomic number, 31, which is what gives me the 39. Okay, so that's how you determine the number of protons, neutrons, and electrons associated with a neutral atom. So let's go on, and I'll talk a little bit about ions. So for ions, let's take, for example, strontium, and I'll just start out with strontium, the atom. So strontium, the atom, you probably get the idea pretty well so far, is 38 protons, 38 electrons, and then the neutrons would be 50, and I would get that by taking the 88, rounding up, minus the 38, and that's where I get my 50. Okay, so now I have an ion. An ion is really a charged atom. What do I mean by that? It's an atom that has either gained or lost electrons. So this ion has a positive 2 charge. That positive 2 charge tells me that 2 electrons have been removed from this neutral atom. So it's just the opposite. Positive 2 means 2 lost electrons. So my number of protons never changes for my ion, because that would change the identity of the nucleus. And we're not changing the nucleus, we're just changing the electrons. So the protons is 38. Okay? And then the electrons are -2, so it's 36 electrons. And then the neutrons for this. Now remember, how do we find the neutrons? We're going to take 88 minus the 38 to get 50. That doesn't change either. The only time that changes is with an isotope, and we'll talk about that in a few minutes. So important to note that when you lose electrons, you form positive ions. But it's the metals from the periodic table that want to form positive ions. We'll talk about that further. And then it's the non-metals from the periodic table that will form your negative ions. And so they have special names. Positive ions are called cations. There's a positive ion, it's called a cation. Negative ions are called anions, and the way that a negative ion forms is by gaining electrons. So it's going to become more negative. And I have one little example here of a negative ion. So for bromine here, I have a small number on top, it's 35 protons. Okay, my electrons, this is the neutral, is 35, and my neutrons would be 80 minus 45, which gives me, 80 minus 35, which gives me the 45. Okay, so for this one, protons, they don't change. Protons identify what the isotope is. So, what the atom is. So that's 35. Now it's a negative ion. Bromine is a nonmetal. It's going to gain electrons. So it's a charge of -1. If you just see the negative there, sometimes it will just have a negative. Sometimes you'll see the -1. And that means that I have 1 extra electron, 36, and the neutrons, again, don't change from the neutral atom. I'm going to stop there.